Hi everyone, this video is where we discuss the derivatives of logarithmic functions. And at this point in the semester, this is a point where I like to take a break and pose a little bit of a brain teaser. And so I invite you to really think about these as we go through them here. You remember the power rule. So when we say, let's take the derivative with respect to x of x cubed, you know that this is 3x squared. And this next one, we're talking about the derivative with respect to x of x to the second power, x squared. This one must be 2x to the first power, which we also just call 2x. And next, if we take the derivative with respect to x of x to the 1 power, this would be 1 times x to the 0 power. 1 minus 1 is 0. And this would be 1 times 1, because x to the 0 power is just the number 1. And then 1 times 1 is just 1. And then we have the derivative with respect to x of x to the 0 power. So bringing down the exponent and then multiplying that by x to the power 0 minus 1 gives us just 0. And that's because x to the 0 power is just the number 1, so we're asking what is the derivative with respect to x of just the number 1. And of course the derivative of any constant is 0. Okay, so let's consider this next one. We have the derivative with respect to x of x to the negative 1 power, so this is negative 1 times x to the negative 2 power. And the derivative with respect to x of x to the negative 2 must be negative 2 times x to the power negative 3. And there's really no trick here. I'm not trying to trick you, at least yet. What I want you to see is the power rule as, applied to some natural numbers. So we did x to the third, x to the positive 2, x to the positive 1, x to the 0, x to the negative 1 power, and x to the negative 2 power. I want you to just recognize sort of the pattern that happens with the power rule and have that in the forefront of your mind. So with that primer, let me introduce you to a new concept. And this new concept that really is a concept in calculus that we'll bring up again, especially in the second half of the semester. It's called the antiderivative. And just like it sounds, antiderivatives are the opposite of taking the derivative. And to denote what the antiderivative is we use this little tall, long squiggle. So it's kind of like an S, but like a lot taller than a typical lowercase s. And what this is saying, where it says little squiggle x to the negative 3 power dx, what this is saying is find the antiderivative of x to the negative 3 power. And again, what this is asking is, what function is there so that whenever I take the derivative of that function, it will give me x to the negative 3. What function is such that when I take the derivative, I get x to the negative 3? Well, let me scroll back up to the previous page and point out that whenever I took the derivative with respect to x of x to the negative 2 power, I got negative 2 times x to the negative 3. So that's pretty close to what I wanted. And maybe if I doctor this up a little bit and change that function, maybe I actually could get just x to the negative 3 without that negative 2. In fact, maybe what I should do is just divide here by 1 over negative 2, or sorry, maybe I should divide by negative 2, which means multiplying by 1 over negative 2. And so let me try that. Let's see if that gives me exactly what I want. So I'll bring down the 2, and I'll get negative 1/2 times positive 2, or sorry, it should be a negative 2, shouldn't it? Times negative 2 times x to the negative 3 power. And negative 1/2 times negative 2, well, that actually has 2 minus signs, so that will become positive, and then 1/2 times 2 is just 1, and so this is x to the negative 3. So then when I ask you about the antiderivative of x to the negative 3 power, this is saying, well, the antiderivative should be negative 1/2 x to the negative 2. Because if I take the derivative of negative 1/2 x to the negative 2 power, I get x to the negative 3 as the derivative. This is what we mean by the antiderivative, is we're just sort of doing the opposite. So I'll let this be negative 1/2 x to the negative 2 power. Okay? Doing pretty good. Let's move along, and I see that I've clearly made a typo on my notes, so let me correct this to what it should be. I'm not trying to ask you the same antiderivative 3 times, but what I meant to ask was the antiderivative of x to the negative 2 power then, and then also the antiderivative of x to the negative 1 power. Okay? So if I take the antiderivative of x to the negative 2 power, the thing, or the function that's going to make this happen is going to be negative 1 x to the negative 1 power. Because think about this. If I actually take the derivative of negative 1 times x to the negative 1 power, you know, that's negative 1 is going to come out in front. It'll be negative 1 times x to the power negative 1 minus 1, which is x to the negative 2, which is then just x to the negative 2. So that checks out. This antiderivative is actually correct. And I don't have to put the 1 in front. This could just be, you know, minus x to the negative 1. And obviously it's the same thing, multiplying by 1. But in any case, let's now take a look at this. And just for a moment, appreciate the pattern that we have. If I'm trying to take the antiderivative of x to the negative 3, it sort of boosts this little x factor into x to the negative 2. And if I take the antiderivative of x to the negative 2, it sort of boosts this to x to the negative 1. And so now pause the video and take a moment to think, what would be the antiderivative of x to the negative 1? Now I'm moving on because I've assumed you've paused the video and you've really thought about this, and I hope you've come up with your own answer. That's the way that we learn math, is by struggling with difficult problems and thinking really hard about it. And assuming you've done that, let's proceed. And I want to point out that a lot of students do this. A lot of students say, well, the antiderivative of x to the negative 1 power, I must be going up in my exponent, so going up from negative 1 gives me x to the 0 power, and then, you know, maybe it has something times x to the 0 power, you know, as just a good guess of what's going on here, right? Well, let's think about that for a moment. If I take the derivative of something times x to the 0 power, this is like, you know, taking the derivative of something times 1. Because maybe you need the reminder, but anything to the 0 power is just the number 1. And so we're taking the derivative of a constant. But you also know the derivative of a constant is just 0. And that's not the same thing as x to the negative 1. So, oops. This is clearly not the correct answer. And the correct answer then is this. It might seem kind of weird, but the antiderivative of x to the negative 1 power is natural log x. Actually, if we're being very specific and technical, what I should tell you is that this is natural log of absolute value of x. And that should seem pretty weird. If it doesn't, I don't think you're thinking hard enough about this, right? Because we developed this power rule, this derivative power rule, where if you're taking the derivative of x to some natural number, you're taking the derivative of x to some whole number or some counting number, you always end up getting x to some whole number back, right? We have this nice pattern where x just decreases the exponent by 1 each time. And yet, whenever we get to here, what we're doing is we're taking the antiderivative of x to some integer power, and what we're getting out is not a constant times x to some integer power. This is really the only exception. This is really the only place where you take the antiderivative of x to an integer power, and you don't actually get back some constant times x to an integer power. So that's the weird part. This is correct but weird. So let's point that out. And I'll summarize real quick. In this blue box here, these are all things I expect you to memorize. And I'm serious about that. Memorize that the derivative of the natural log function is 1 over x. And we just discussed this. Because remember, 1 over x is equal to x to the negative 1 power. That's just how the negative exponents work. And in fact, if I have 1 over x to the negative 2 power, that's just x squared. So, be aware of the way that negative exponents work. And this is the derivative of the natural log function. So our topic today is the derivatives of the logarithms. And logarithms can have different bases, right? So we can have logarithm base 2, logarithm base 10. Those are both very common logarithms to use. But in fact, we also have the formula for the logarithm with any base. So a means any base is just 1 over natural log a times x. And one last thing I'll say before we move on is that when you see ln of x, that is ln of x, this is the natural logarithm, and this is just the logarithm with base e of x. And again, remember that e is just a number. It's just a constant that's somewhere around 2.718. Not exactly 2.718, but it's close to there. Okay, so we've memorized what's going on inside this box. We know our logarithm rules. I sometimes will admit that I get off in the weeds pretty frequently with explaining why the math works. And I'm pretty passionate about that. I want my students to really appreciate that math is not just a silly, disjointed set of rules, but actually there's a reason behind everything, and everything can really be explained and dived into. Sometimes I get off in the weeds doing this, but I actually want to show you this one because I think it's just really elegant and simple and neat. And the way that we know the derivative of the natural log function is 1 over x sort of sneaks up on you. And it's really kind of, it's weird because it's tricky to pinpoint where it comes about. But let's do this. Let's set a function y, where y is just the natural log function. And suppose we want to find the derivative of the natural log function. So what we're looking for is dy dx. And also remember in the last lesson, we learned about this. We learned that e to the power x is the only function where it is its own derivative. And so remembering this, we're going to sort of start and hopefully arrive at the conclusion that the derivative of the natural log function is 1 over x. So I'm going to write over here y is equal to natural log x. Then what I'm going to do is actually I'm going to take e to the power y, so e to the power the left side of the equation, and then I'm also going to take e to the power the right side of the equation, just like this. So if those things are equal and I have the same base, then this equation should still be true. And hopefully you remember from your algebra class that the exponential base e and the logarithm base e are inverse functions. And so that means that if I take e and I compose it with the natural log, this is just x. And likewise, if I have the natural log of e to the power x, this is also just x. This is what it means to be inverse functions. And so if you don't remember this, maybe review your algebra course materials on inverse functions. That's pretty important. So whenever I see e to the power natural log x going on here on the right side, I'm going to replace that with just an x. And I'm doing that because, again, this is sort of the definition of what the natural log really means, is that whenever you take e to the power natural log x, you actually just get the identity x back. Okay, so we're moving along. We have e to the power x equals x. Now I will go about taking the derivative of both sides of this equation with respect to x. And on the right side of the equation, this is pretty simple. The derivative of x is 1. That's a power rule if you look really closely at it. On the left side of the equation, this is actually a chain rule because remember, y is a function of x. And so using the derivative chain rule on the left side gives me e to the power y times the derivative of that inside function with respect to x. So remember, chain rule says that when I have a composite function, I take the derivative of the outside function times the derivative of the inside function. And so this is me taking the derivative of the left side of the equation here. Well, now let me take dy dx on the left side and just divide both sides of my equation by e to the power y. So now my right side of my equation looks like 1 over e to the power y. And that's a pretty neat result. And maybe your brain is already jumping ahead of me, but I'll rewrite it up here. Dy dx is equal to 1 over e to the power y. But then we remember that we said y is just going to be natural log of x. So this lets me say dy dx is equal to 1 over e to the power natural log of x. Okay. On the left side, the derivative of y with respect to x, well, we're saying that's the derivative with respect to x of, well, again, making use of this definition, natural log x. And look in the denominator, where I have e to the power natural log x. We said a moment ago that this is also just x, so this is going to be 1 over x. And that, as a result, that looks familiar. This is what we wanted to prove. Proved with 2 O's. Sorry, this is proved. But I couldn't decide if I wanted to write proved or if I wanted to write proof. But what we've just done is we've shown proof of this particular derivative. And I just think that's neat. So, you know, excuse me for maybe spending too much time on the explaining side of things, but I think it's good for students to see it and appreciate where these come from. These aren't just a wild and crazy set of rules that we just made up for fun, but these actually come from some sort of logical, reasonable explanation. All right. Example 1. And again, the rest of this video is going to follow the pattern where I show you an example and then I expect you to work a practice problem, and then we compare answers after that, because you really cannot get good at math without practice. So example number 1, I have a product, so I'm going to use the derivative product rule, and the product rule tells me that my derivative of a product of functions is going to be f prime g plus fg prime, where my f function is going to be this nice nice logarithm base 2 function, and then my g function is going to be x squared plus 1. That means that f prime will be, 1 over natural log 2 times x, and also g prime is going to be 2x. So I have f prime g. In other words, I've got x squared plus 1 over natural log 2 times x. That would be an f prime g, and then plus fg prime. So plus log base 2 of x times g prime, so times 2x. That is your answer. That's your derivative. So now this is the part of the video where you pause and you write down practice number 1 and you give it your best shot and really try to come up with the correct answer, and then unpause the video. And at this point, I'm assuming you've done that and given it your best shot. So I'll show you the solution now to practice 1. You can compare it with your solution and obviously investigate if you got it wrong. And if you got it right, then obviously awesome job. So again, product rule. This is my f function. This is my g function. So I have f prime g plus fg prime. So f prime is going to be 1 over natural log 10 times x. That will be f prime, and g is just going to be 5 minus 3x cubed, plus, when I do fg prime, this will be not natural log, logarithm base 10 of x, and that's f, and then I need g prime, and so g prime is going to be, let's see, negative 9x squared. There we go. Hopefully that's your solution. All right, example 2. I've got the derivative with respect to t of natural log t over t squared. And so this is a quotient of 2 functions. So I'm going to use the derivative quotient rule, which is saying when I take the derivative of f divided by g, this is now f prime g minus fg prime over g squared. So f prime g, well, f prime is going to be 1 over x, and then g prime is going to be 2t. Sorry, I'm not dealing with x's, I'm dealing with t's, and that's sometimes difficult to remember. So f prime is 1 over t. So this is going to be 1 over t times t squared. So that will be, well, I'll just write it out. 1 over t times t squared minus f times g prime. So f is natural log t times 2t, all divided by g squared, which is t squared squared. All right, up top, t squared times 1 over t is just t. And I've got a t in my second term too, so let me just factor that out. This will be t times 1 minus natural log t times 2. Let me rewrite that. It's bad handwriting. 1 minus 2 natural log t. It's supposed to be 1 minus 2 times natural log t. Okay, took me a few tries on the handwriting. And then divided by t to the 4th power, because t squared squared is t to the 4th, and then I'll cancel one of the t's from both numerator and denominator, and get 1 minus 2 natural log t in the numerator divided by t cubed in the denominator, and that is our simplified answer. This is the point in the video where you pause, you try practice 2, you give it your best shot. Don't unpause the video until you're done and you're ready to compare answers. At this point, I'm assuming you're done and ready to compare answers. And so again, we're talking about quotient rule. This will be f prime g minus fg prime over g squared. F prime is the derivative of the numerator, which is going to be 3 times 1 over t, times g is my denominator, so times t, minus f, which is my numerator, 3 natural log t, times g prime, which is 1 over g squared, which is now t squared. Okay? I've got a 3 I can factor out in the numerator, and notice the 1 over t and t cancel. And so this is going to be 3 times 1 minus natural log t over t squared. That's your simplified answer. Here's example number 3. And in example number 3, this is again a quotient rule problem. This time my logarithm is in the denominator. But otherwise, same idea, f prime g minus fg prime over g squared. Since f is my numerator, f prime is just going to be 5y to the 4th minus 3y squared. g is just my denominator, so g prime is going to be 1 over natural log of 3 times y. So now we're ready to use my quotient rule formula. F prime g is going to be 5y to the 4th minus 3y squared times log base 3 of y, minus fg prime is minus y to the 5th minus y cubed times g prime, which is 1 over natural log 3 times y, all divided by g squared, which is going to be log base 3 of y squared. Okay, we can simplify the numerator just a little bit. Because notice I have a 1 over y over here, multiplying the y to the 5th minus y to the 3rd. And so this is cheating a little bit, but I'm going to get rid of that y in the denominator and make that 5 into a 4 and make that 3 into a 2. So I just divided y to the 5th divided by y is y to the 4th, and y to the 3rd divided by y is y to the 2nd. And now I can, I don't know, that's probably as simplified as it gets, because if I distribute these logarithm coefficients and then I combine like terms, that's going to look just as messy. And so this is really as good as it needs to be, in my opinion. So you can leave it just like this. This is the point in the video where you pause and you try practice number 3 on your own, and don't restart the video until you have a solution and you're ready to compare answers with me. At this point, I've assumed you've tried your very best and we're ready to solve this with my quotient rule formula. We've got f prime g minus fg prime over g squared. And so f prime is the derivative of my numerator, and so that derivative of 2 to the y, okay, we've got to remember what we learned last video. That's going to be natural log 2 times 2 to the y. And also the derivative of negative 2y to the y squared is negative 4y. So that's my f prime times g. G is log base 5 of y minus fg prime. So now f is 2 to the power y minus 2y squared, and g prime is going to be 1 over natural log 5 times y. Divide the whole thing by logarithm base 5 of y squared. This is a mess. Maybe there's a way to simplify it, but I'm honestly not interested. If it's this complicated, just leave it like this on your exam, and that would be just fine. Okay. Here's example 4. So in example 4, we've taken the derivative with respect to x of natural log of x squared. And so this is when we need the derivative chain rule. And so I'm going to set y equals natural log x squared. And so whenever I take the derivative of y with respect to x, according to chain rule, I can take the derivative of y with respect to u times the derivative of u with respect to x, and I just get to decide what u is going to be. And I just have to, it's up to me to choose a really convenient choice for u. So let me just let u be x squared, because if I let u be x squared, now y is just natural log of u. And that's pretty good. Now let's find first the derivative of y with respect to u. And so the derivative of y with respect to u is just the derivative of the logarithm, which is going to be 1 over u. And now let me find the derivative of u with respect to x. And so du dx is just the derivative of x squared, so that's 2x. Putting all of this together, back over here, I have dy dx is equal to dy du, which is 1 over u, times du dx, which is 2x. And remember that u by definition, is just x squared. So this is 1 over x squared times 2x. And so what I'm looking for here, the final answer, when I cancel an x in the numerator and an x in the denominator, is 2 over x. So that's pretty neat. Practice number 4 is your chance to pause the video and give it your best shot, and don't unpause the video until you have really tried your best and you have an answer that you want to compare with mine. So at this point, I'm going to move ahead, assuming you've tried this using the derivative chain rule, and I can tell you that this is going to be the derivative of the outside function, which is 1 over natural log of 2 times 4 minus 3x squared, all times the derivative of the inside function, which is actually going to be negative 6x. Okay, so hopefully that was your answer. Here's example 5, our last example of the video, and we have the derivative with respect to t of square root of logarithm base 10 of t. So this is again going to be a chain rule problem. And remember, a chain rule is saying that take the derivative of y with respect to x and say that's just the derivative of y with respect to u times the derivative of u with respect to x. And I get to choose what I want u to be. So I'll just let u be the log base 10 of t. And that is a good choice of u because if I let y be the function square root of log base 10 of t, now y is just the square root of u. So first, we say what's the derivative of y with respect to u? Well, square root of u is just u to the half power. So power rule tells me this is going to be 1/2 u to the negative 1/2 power. Good. And move on to du dx. So taking the derivative of u with respect to x, well, this derivative we've just learned is 1 over natural log 10 times t. Okay, so putting it all together with my derivative chain rule tells me that my dy dx, which is what I'm looking for, is equal to 1/2 u to the negative half power times 1 over natural log 10 times t. I still need to get rid of my u because it's not good to leave the u in your final formula for the derivative. So we write dy dx is equal to 1 over 2 times log base 10 of t, all to the negative half power, times 1 over natural log 10 times t. Kind of a messy answer, but there we go. Practice 5 is again for you to pause the video and give it your best shot. I'm going to continue now, assuming you've already tried your very best here. And so let's give the answer for practice 5. Again, this is chain rule that we're using. My inside function is going to be natural log of 5t. My outside function is going to be x to the power, or sorry, t to the power 3/2, if you will. So the derivative of my outside function is going to be 3/2 of natural log 5t all to the power 1/2. That's just power rule for my outside function. And then times the derivative of my inside function, so the derivative of natural log 5t, well, that would be 1 over 5t. But actually, there's an inside function inside that inside function, right? So inside the natural log function, there's also the 5t function, and the derivative of 5t is 5. So these 5s are going to cancel, and my answer here in the end will be 3/2 times square root of natural log 5t over t. Okay, so hopefully these examples were helpful to you, and hopefully you'll feel like you're getting better, and hopefully you spend even a bit more time practicing some examples of logarithms, taking the derivatives of logarithms and also including that in your product rule, quotient rule, and chain rule derivative calculations as well. I'll see you guys in the next video.